Good afternoon, everyone. I hope everyone can hear me. Thank you all very much for joining today's webinar from OEG. My name is Jan-Jelle Huizinga, and I am going to walk you through the subsea technologies that we've developed within our research and development department over the last years. So, agenda for this session, a bit of a background from myself, the birth of R&D, so to say, and why did we start an R&D department in the first place. Some examples on market-driven developments that we've done, a discussion on scalability and how we try to achieve this, some internal-driven development examples, and a small view on what's next and what we're working on. And then we'll have a Q&A session as well. So, background for myself, I started the industry about 14 years ago at the time within Bluestream Offshore as a rope access technician with a background in climbing and a electrical engineering background. This was a good fit to roll into this wonderful world. From there, I moved on to the ROV side of things, where we operate electric ROVs, so that was a good fit as well. So I've done a few years offshore, and then went on to the more technical support side of things, project engineering and detailed engineering as well. So the birth of R&D, it's a bit of a funny story, actually, a fairly simple development that we've done over the last, that was actually in 2016, I think it was, where we have developed a messenger wire hook, which was a very practical example of a development that I've done offshore together with an engineer from our client at the time, where we were doing messenger wire installations. And these messenger wire installations were done with a small ROV, which caused a lot of damages. So we thought of a specific hook design where you can install the hook with a mini ROV on the inside of the monopile, and then also grab it on the outside with an ROV hook. And that way pull your messenger wire through the monopile. Now, this design has since then in the industry been copied by many other contractors that I'm aware of. And I think that was one of the biggest compliments I had, seeing other companies copy your design. So that was really the first start for me to sort of engage in this world of engineering subsea. So a very, very simple, practical, very mechanical oriented solution. But yeah, it was a fun project in itself. So why did we start an R&D department? Many clients have project-specific challenges that require tailor-made solutions. Very specific in the domain where we're trying to move away from diver-based solutions to RV-based solutions. You come up with certainly a lot of challenges that weren't considered to be challenges previously. And there's no generic tooling available, or they're inefficient to combine on jobs. And the last one is fairly important for us, where we're trying to combine scopes of work with larger dive support or RV support vessels. And when you're hitching multiple jobs in a row, and you have to get a specific tool on board for a very specific task of a few hours, and you need to hire in this equipment for multiple weeks, that becomes very cost inefficient. Such examples of such projects are complex NDT, like ACFM wall thickness measurements on complex geometries, but also installation of specific components like vibration sensors, sonars, ICCPs, ICCP reference cells. Those are all installation components that we've built specific tooling for. And also scientific research for the marine biologists specifically. We've done a nice project as well, which I'll touch on later. Tooling development for a larger market requires standardization to make it scalable. Now, what do we mean with that? In the industrial automation, there are many vendors, many suppliers of hardware and software, or a combination of the two, that have designed their product to sell to a larger client base. But if each client has their own specific needs, or each vendor creates their own standards, then nothing is compatible with each other, and that creates a very complex task once you start to grow, say a factory, for example, and you want to combine different systems. Then standardization, specifically on hardware and software and communication protocols, is very important. Now, having a scalable approach there and having standardization reduces development time significantly. And these development times, again, are mainly focused on the hard and software side of things. And if you have a niche market, which the subsea sector is by default, then it's very difficult for larger vendors to create standards on this, because that's a costly process as well. So you need a larger market to do this on. So that's my approach on why the subsea domain is not standardized that much in that sense. A few market-driven examples I'll show you now, and one of them is a combination of 3 tools, or a sort of a continued development of 3 tools, which is the arthropod, a large U-shaped clamp, the GobiSox, a vehicle that adheres to surfaces by suction, and then the Mecanum Crawler, which is the latest of the 3. This specific tool has been designed to perform weld inspections on complex geometries. These weld inspections are mandatory for asset lifetime extensions, something that's becoming more and more relevant in the North Sea, because more operators want to extend the design life of their assets, and the notified body to approve the lifetime extensions then requires more thorough weld inspections specifically on nodal joints. And this has been done a lot by divers in the past. But doing this on a risk-based inspection with ROV-only campaign requires specific tooling to perform these weld inspections. Now, there are other suppliers in the market who also facilitate such a service, and of course they have their own developed tools for this. But here we really come into the argument I gave earlier, that if you have a specific weld inspection to do, and you need to hire in a party that has such a bespoke tool for 2 weeks for only a campaign that requires a few hours or a few specific platforms, it becomes a very cost-ineffective solution. So that's really the reason that we decided to go down the route of developing this ourselves. Here you can see some pictures of the deployment of the GobiSox on the left, and the arthropod, the Mecanum Crawler on the right. And by the looks of it, you don't see much difference between the two. But if I go back one slide, you can see this device here is quite a bit larger, and it has just straight wheels driving over the circumference of the node. And the other one on the right here has the Mecanum wheel principle, which are omnidirectional wheels. And this one is not able to drive over the circumference, or the circumference of the node, but also, or of the member, but also over the longitudinal side, so over the length of the member. And that's really a big added benefit for this specific device. Put a laser on there, because this device is much more flexible to deploy. You can also see that. I have a small video here. Hope you can all see this, where we're deploying the latest innovation. And here we can deploy it anywhere on the member, and then it can drive itself to the required destination and start the weld inspection. Whereas the GobiSox was very critical, where we had to place the device, and then we only had a limited reach of the probe, of the ACFM probe, to perform the inspection. So this device really gains a lot of flexibility, and the continued development here is really a good example of how we try to push the innovation to reduce our operation time span and decrease the total time of inspections to basically have a more cost-effective solution. Another market-driven example. So as I mentioned, the previous one was also a market-driven example, really a push from the market due to the lifetime extensions. And another push of a market-driven example, another market-driven development was the marine growth sampling tool. The marine growth sampling tool has been developed in cooperation with the Wageningen University. They perform a lot of inspections on the marine growth in the North Sea to monitor the development of this. And this is becoming a very important factor in the future, as there's a mandatory nature inclusive design element. So for the licensing of the build of, for example, wind farms, it's mandatory that the operators include a nature inclusive element there. So they are mandated to inspect the impact of the assets that is caused on nature, and both in positive and negative sense. And by inspecting the marine growth on there, they can prove that they actively cooperate in this. So this is also a tool that a task that used to be done by divers, but with a large push for ROV only operations, both by our clients, but also something that we want to drive ourselves. We've developed this tool, and the functionality of this tool is basically a scraper knife which vibrates and is pushed along the member. So the tool pushes against the member with the 4 pins, and the scraper knife scrapes over the circumference of the member while the knife is vibrating. And in the back here, there's a sample box where a water flow is being sucked through. So all the sample material is being sucked into the funnel here and being stored in a net in the box there. This tool has been deployed on a Tiger ROV, so a fairly small ROV, as you can see here on the right. And it's been tested on one of the wind farms that had a collision in the past of a vessel. So we were allowed to perform extensive tests on this, which was very successful as well. So we're keen on continued development of this tool and continued testing to validate the functionality more and to prove that we can deploy this tool safely without damaging of a coating and adding value for the inspections of the marine growth. So touching on scalability, it's fairly obvious that it's important to be able to iterate quickly through designs, especially if you're testing something offshore and you need to apply any changes that you see quickly without having to redo your entire design process, which is mainly a hard and software focus. Mechanical design is proven to be fairly flexible. The costs of getting a part reproduced or a machine slightly differently configured is not the most critical thing. It's more critical that we can reuse hard and software blocks and connect this to an open platform as much as possible to be able to quickly develop new tools. And what we try to do is to gain full control of critical components with minimal vendor lock-ins. The last thing you want to have is an offshore operation, something breaks down, and your spare is a 24 months lead time, which is not something that it's uncommon. So what we've really aimed for was an open platform approach. So try to follow industrial standards, what I explained in the beginning, as much as possible, where the industrial automation have already defined a lot of open standards and already developed a lot of open or hardware that connects to this platform. So we can use common off-the-shelf components, and this really reduces the development time. However, this unfortunately was not possible. We cannot find components or hardware that has the full functionality that we require. So we had to develop our own electronics as well. But we always said that we want to keep connectivity to that open platform. So we developed all our electronics to a standard that's common in the industry to ensure that we can quickly reuse those components without having to change hardware or software on that. So as I mentioned, the industrial automation sector already has some established platforms, common interfaces, and no vendor lock-in on most hardware. So you can always find a different supplier, for example, for motion controllers, variable frequency drives, all kinds of sensors. There's many components on the market able to connect to these common interfaces. And it's often proven technology as well. working in robust, in harsh environments, so designed for robustness, say vibrations or moist or all industrial environments, heat, for example. So often the technology is also designed to endure. And it's also any new sensor that come on the market within this specific domain is also capable of connecting to these interfaces. So also new equipment that comes on the market is quickly integrated. Disadvantages, as I mentioned, the subsea domain is hardly represented to my experience. So a lot of vendors, they create their own little tool with their own little proprietary hardware and software, and it's difficult to integrate on that. Specific requirements for control tasks such as thrusters, valves, lights, zoom focus, functionality on cameras, that's not something that the industry uses from a factory point of view. So there's no hardware available for that, or hardware that could be used is often too large to put in the subsea housings. So they rarely follow these standards. Now, how did we overcome these disadvantages? As I mentioned, we developed the hardware fully in-house, so we have full control of the peripherals, but we kept connectivity to these standards. That way we could reduce the footprint of hardware as much as we could with no excess functionality, yet obtain all our hardware and software blocks that we've already built for previous tools. Quick iteration cycles are that way possible. So new requirements for tools are quickly processed, and I have a nice example of this later. Keep it simple. Equipment for offshore needs to be maintainable. We have a few very capable technicians offshore, but they are not IT specialists. And what you see more and more with hardware and connectivity, that you need to be IT specialists to be able to connect this to any new platform and configure it. And all this complexity we wanted to remove from the equation so anyone can replace a piece of hardware. And then obtain the advantages of the industrial network with the flexibility of our own custom electronics design. So this is one example of a PCB. In this case, it's a thruster power PCB, which we developed, but we've developed around 30 PCBs by now, with different functionality for specific requirement tasks, but all with the connectivity to the same platform. So yeah, this is a nice example of a board where we can isolate thrusters, read fuse statuses, read currents, all functionality that's not possible in our current RV design. A good example of an internally driven development is ICCP SAM. ICCP SAM, for those unaware, it's been posted on LinkedIn multiple times already. But it's a device to install ICCP anodes from the inside out from monopiles. An issue that we see more and more offshore is that ICCP anodes are fragile because they're mounted close to the surface. As you can see here on this inspection video is a damage of a specific anode. These anodes are installed externally on the monopiles. We have come into contact with CORROSION. CORROSION is a company that supplies ICCP anodes, and we have asked CORROSION, or CORROSION have asked us actually, to look into the possibility of installing ICCP anodes from the inside out. And that's how we came up with the ICCP SAM, which stands for Subsea Assembly Method, where we have basically taken a chunk of steel, mount some thrusters to it, as you can see in the picture on the left, and then see if we could operate basically fly a full ICCP anode like a torpedo. And this has been an extremely fun project over the last 2 years, where we have developed the tool that you see now on the right here, which is connected to an ICCP anode, a large tube of 2 meters with an anode in front. And we launch this from the inside out in a monopile, and then find the installation hole, and then basically lock the anode in place and retrieve it. As I mentioned, this project has been going on for 2 years, but as we speak, we are actually running the first campaign of installing these ICCP anodes. And so far we have finalized the first 2 monopiles, so very exciting news for us. You can see that here, some pictures of the actual installation ongoing, where on the left here we're launching the system in the monopile, lowering it below the airtight platform and flying the ICCP anode. with the control station here. And here you can see a video of the ROV on the outside of the monopile, observing the installation of the anode and performing the S-last survey. So it's very, very exciting for us, this development. But yeah, as I mentioned, one development leads to another. And with this ICCP tool, we had to develop our own torque motors that you can see inside here. Electric subsea torque motors capable of torquing up to 680 Newton meters. And that led to the development of our own torque motor, which we can deploy on relatively small ROVs for valve operations, for example. So as the hard and software was fully ready, we basically designed an interface which was in line with the subsea standard of valves, and deployed it with one of our Panther ROVs, and did a valve operation for Total in a turnaround time of only a few weeks, where in comparison with original torque tools, hydraulic torque tools, you have a very heavy tool, which is has to be set on the surface with hydraulic pressures and flows. With this particular tool, we could set the torque level and speed in the software and measure this real time as well. So it's a very flexible tool, and as far as we know, it's the smallest torque motor on the market within the range that we can supply torque for. So 680 Newton meters. So that's a nice example of a continued development of the hardware that we've built for specific tools. Another development that we're working on is an ROV control system. So this is really an internally driven development as well, where we said, okay, we operate a fleet of ROVs, but the control system in these ROVs is outdated. They're reliable, but they're no longer updated by the supplier. There's no diagnostics on it, no human-machine interface, no auxiliary control, and no station keeping. And also there's no option of logging in remotely. These are all features that you get nowadays when you purchase new ROVs, but owning roughly 20 of these ROVs and not having a retrofittable system on the market, we said, okay, we've developed so much hardware and software now, we can also take this task on ourselves, as we have so many of them. So we have designed a software interface, full hardware stack to develop to control the ROV and operate it as much with as much similarity as possible to keep this new system very similar for all the pilots that we have offshore. So from an operator perspective, there's not a lot different in terms of controlling the ROV, but all the functionality that I just mentioned is integrated in this. So it has the ability of station keeping with the DVL. It has the diagnostics. So every PCB has health monitoring, and it's fed back to the operator. So in case of any errors going on, the operator is likely to find the error already when the ROV is being recovered to surface. And everything, again, is connected to an open standard system, which is capable of integrating with industrial, robust hardware. So what's next? The developments that we've done so far, scale them up from OEG Den Helder or OEG Netherlands to OEG worldwide. What other challenges do we have with the merging of Bluestream and OEG to see where we can assist and where we can use our developed technology within the other departments, and how can we integrate everything so that there's a common interface for the operators to use. So get a recognizable platform, a recognizable interface to be able to send personnel from one bit of kit from one asset to another without having to do a full new training on the functionality of the tool, because there will be a sort of a natural transition, because there's similar hardware and similar software used. It's just slightly different functionality of the specific kit, but it will be able to transition personnel from different projects much quicker. So that's a key thing that we're going to work on. Of course, to expand the new ROV control system, which I just mentioned, which is actually currently deployed on one ROV as a prototype. and it's being used a few weeks now offshore as well with great success. So that's good to mention. So we're looking at expanding this to our other RV systems as well. And on top of that, we're also looking at an internal development for our tether management system. It's a bit more technically in depth, but an RV that's being deployed through a TMS. We have quite a few of those for vessel-based systems, but on that TMS specifically, we also had a lot of comments, so we decided to develop this ourselves. But that's still a fairly new project, so there was not a lot to share on yet. But yeah, those are a few of the topics that we're also looking into in the coming years. So that was really it from my side. If there's any questions from yourselves, be happy to answer them now, or otherwise perhaps later over email or phone. If you feel free to reach out.
We do have one question that's come through in the Q&A chat box. Hopefully you can hear me. The question says, will the R&D department be expanding as a result of industry demand for more diverless solutions?
That's a very interesting question. Well, looking at the historical data, where it was just one engineer, say 5 years ago, we're currently with 5 engineers in the team. So in that sense, yes, we're expanding. I think especially looking at the scalability going forward to the other companies within OEG, there's a definite potential to grow that team even more. So I would say yes.
We do have another question as well from another attendee. It's quite a long question, so I think best to get back after the webinar because it might need a bit of a more in-depth answer. So for Ido, we'll get back to you after the webinar. But that's all the questions from the chat box.
All right, perfect. Well, if there's no further questions, then I would say thank you all for your attention and hopefully speak to you soon.